All right, let's start. Folks, this is Dr. Yuzo. This is EC 341 Power System class. This is our 10th lecture. First, can you guys hear me? And also being able to see my screen?
Yep.
All right, thank you. Thank you. All right, so if so, then let's move forward. So first, any questions regarding the end of the last lecture? We talked about this example 3, which is very important, especially you need to be very clear on these concepts. Okay, to be very clear on this concept. So different sequence at different phase. So we have 3 phases and 3 sequences. So 3 by 3 up to 9 components. 9 components. So which one I'm asking for? Okay, because you can't list all of them there in the exam. Okay, and that way you can lose points because that's considered as don't understand what I'm asking for. Okay, so make sure you do understand which component is being asked, and then put maybe 2, maybe 3, maybe more of them into the same graph, maybe according to the requirement in the problem. Okay. Any questions regarding this? Probably is not challenging, is not very challenging to you guys, but this is basic concepts of the different sequence, very important in power systems. Any questions, any concerns? All right, if this is all good, then we move on. Okay, today we're gonna talk about the per unit. I mean, we have learned that the basic concepts. However, today we're gonna have some examples to do, and then if any questions, just let me know. And the rest of the time, just for you to maybe repeating the review of midterm 1. For me to repeat the review of midterm 1 for you to ask questions. Okay. So before going through the example, obviously we need to review the basics. Now, this is the page we had before when we talked about the per unit concept for the first time. There's some very important thing you need to be very careful. Like the red color emphasized here. The per unit value is phasor or say complex number, right? Generally speaking. Okay. It might be real number, however, most of the scenarios is a normal phasor. In other words, the per unit value is not magnitude only. Okay, be very careful. The per unit value just equals to actual value divided by the base value. The actual value is a phasor, whatever, maybe impedance of 10 plus 10J, 20 minus 30J, something like that, or current of 10 minus 20J, so normal phasor, or say complex number. That actual value divided by the selected base value. The selected base value, you need to be very careful. Base value is magnitude only. Okay, the base value cannot be a phasor or complex number. If you mess up the calculation, they're very likely to because of this mistake. Okay, your base value is a real number. It's magnitude and the magnitude only. Okay, be very, very careful. Be very, very careful. Okay, and this is very important. So based on that, the per unit of power equals to the actual power divided by the base power. Per unit impedance equals to actual impedance value divided by impedance base value. And so on and so forth. Right? This is a very easy concept. The next, you need to be very clear. How to choose or say how to select those base values. Right? We have up to 4 base values you need to take care. Up to 4. Base power, base impedance, and base voltage and base current. Okay. How to find them? How to choose them? Here we go. Okay, I'm using the star to emphasize. So here, first choose the magnitude of the three-phase apparent power as the base power. And then choose the magnitude of the line voltage RMS as our base voltage. So first of all, you need to choose two, base power and base voltage, based on which we are deriving the base current and the base impedance. So we're going to have 1, 2, 3, 4, up to 4 base values to describe the entire system. Okay. And the formula here, obviously, you need to have them ready for the exam. The base current equals to base power divided by square root of 3 and times the base voltage. The base impedance equals to the base voltage squared divided by base power. I'm using, once again, here to emphasize, base power is three-phase apparent power. And the base voltage is line voltage RMS value. Okay. Be very, very careful. Be very, very careful. And all of those four base values are magnitude value, magnitude only. Okay. If these are in mind already, then here is the calculation. Here's the calculation problem. What we do about the calculation is actually the so-called change of the base. What does it mean is you have system 1 and system 2. Obviously, in system 1, you have base voltage, power, current, and impedance, one set of base values. In system 2, you have different base values. Well, maybe some of them are same as system 1. However, it's still considered as different system, different set of base values. Does it make sense? So based on these base values, respectively, you are looking for the per unit value. For example, in the system 1, you know maybe the per unit 1 value is given. It is equal to actual value divided by base value 1, right? And in system 2, per unit 2, of course, different per unit value here, not equal, because we have different base values. However, the actual value is what? Same. No matter which system, the actual value is same. 10 ohm remains as 10 ohm. 100 plus 100 J current ampere remains as the same. Okay? Remains as same for system 1 and system 2. It doesn't matter. Actual value is the linkage between different systems. No matter how you change your base values, your actual value, of course, cannot be changed. Otherwise, it makes no sense. Okay. So from the first system, we probably be able to derive the actual value and then plug this actual value into the second system, and then you got the per unit value of second system for the same actual value. Impedance, voltage, power, or current. Okay, this is the idea. This is the idea. And so first of all, any questions regarding these ideas? Any questions? The concepts, anything? Or if they are clear, then go ahead. Let's do examples. Okay, let's do example. And after today's lecture, probably this problem in the exam should be ready for you. It should be ready for you. Okay. The first example, of course, per unit system. First example is saying in a three-phase power system. So Y connected. Phase peak voltage is 179.6 kilovolts. has our impedance of 1.5 angle 30 degree per unit. Here it's telling you the base power is very nice. It's just a 100 mega VA. And then find the per unit value of the same impedance in another system with line voltage RMS 345 kilovolt and 200 mega VA apparent power. Yeah, give you guys 1 more minute to copy the problem. All right, let's take a look at the problem here. By reading this, in your head again, it's in your head you have 2 different systems, right? It's system 1 and system 2. System 1, obviously, right? System 1, what do you have? Per unit 1 value, right? What is it? It's there, right? And what are we looking for? Does it make sense? Just looking for this guy. What else we have? Y connected phase peak voltage is 179.6 volts. So what can we know is obviously we need this two, right? Because we are talking about what? We are talking about impedance. Therefore, we need to derive what? ZB1. Does it make sense? Same thing here in system 2. We need VB2 and SB2, based on which we derive ZB2. Because VB and SB need to be selected first, right? So you can derive the ZB and IB. However, we don't need IB here. At least it looks like we don't, right? Because we are looking for the impedance. Then who is VB1 and who is SB1? Well, the SB1 is very easy, right? The problem is telling you the base power. It's very clearly telling you the base power is 100 mega VA. Be careful, it's mega VA, okay? It's not VA. And also be very careful, the unit. The unit makes perfect sense. It has to be apparent power, okay? it has to be apparent power. So the unit must be VA. Okay. If the given is three-phase power like 100 megawatt, you need to find the S. You need to find apparent power. But here, it's already VA, and also it's telling you the base power. It is the 100 mega VA. So nice. We just use it. Then what is the VB1 then? According to what we learned, it must be line voltage, and also it must be RMS value. And also it must be magnitude. Well, several things you need to be careful. Once again, line voltage, RMS value, and also magnitude. Okay, be very careful. The nice thing is the given is just the magnitude only, so we don't need to worry about it. However, it's what? Phase voltage. It's not line voltage. And also, it's not RMS value, but peak voltage. So what do? Well, first, 179.6 need to be times square root of 3, right? When it's supposed to be times square root of 3 with angle of 30 degrees. However, once again, we just need magnitude for base voltage, right? So we don't involve that 30 degree, okay? So now is line voltage and also peak value, right? This is the peak. We need what? RMS. Right? And also be careful, the unit is a kilo, as kilovolt, like it's kilo. Here we go, right? Here we go. VB1, SB1, done. ZB1, just copy the formula, which is equals to what? VB1 squared divided by SB1, right? And this is algebra is very straightforward because once again, this is just operation among the magnitude real numbers, right? So what is it? 484 ohm. Okay, if you do the calculation yourself, you should end up with 484 ohms. Okay, also be careful, this kilo and mega. Okay, this is of course matters. By here, you can go jump to the system 2 to take care of VB2 and SB2, and also ZB2. You can do that. But I'm just looking for the actual value. Actual value equals to what? Z per unit 1 times ZB1, right? The per unit 1 is here, 1.5, angle of 30. ZB1 equals this. So you end up with what? This impedance is equals to 726 with angle of 30 degree. And this is actual value. Actual value of system 1 is also the actual value for system 2, right? We don't need to worry about it. So now it's time to jump over to the system 2, where, of course, if you did that before this actual value, that's fine too. Okay. So VB2 equals what? You need to carefully read the problem again. So VB2, the information is here. So another system, which is system 2 with line voltage. Okay, nice. RMS value, nice. 345 kilowatts. Magnitude only, nice. Right. And here, 200 mega VA power. Okay. So here, of course, the problem should tell you this is 3-phase. It has to be 3-phase. 3-phase 200 mega VA power. By the unit, we can tell this is apparent power. So it's just a 200 mega VA. Right. So system 2 is fairly easy. Very easy. We still need to derive the ZB2, VB2 square SB2, and then certain amount of base value we need to follow. So now what we have is a base value of system 2 and actual value. Okay, then the rest of the thing very easy, right? Per unit value of system 2 equals to actual value divided by the base value from system 2. Very easy algebra. And of course, be careful, the per unit is per unit. The base value units are SI, right? SI unit, watts, ampere, VA, ohm, and actual values units. Of course, we know what is it, right? Done. Problem is done. So the key is what? Just the here. Okay, just the here. Don't mess up the here. Read the problem carefully. Right? Read the problem carefully. Read the problem carefully. Right? Three-phase magnitudes of line voltage RMS value is the VB. Three-phase apparent power is SB. Magnitude. Right? So select the right VB and SB to derive the IB and or ZB as required. And you need to read the problem carefully. And the problem is asking is talking about a current or impedance or voltage or power. Any questions? All right, if this is fine, then one example you guys go ahead to do on your own. And then I will present the solution. Example like this. So a three-phase system why connected source base voltage is kilovolt. What RMS was three-phase power of 0.2 megawatts power factor of 0.9 leading. a current in this system is 1 per unit. Find the per unit value of the same current in another system is three-phase line RMS teach of 345 degree kilowatt and 2 mega VA three-phase power. All right. If the problem has no, I mean, if you have no questions on the problem itself, then just go ahead. Give you guys maybe 10 minutes to try this over, and then maybe you see the solution. Okay, go ahead. Is there anyone could actually get any value, any result, by any chance? Uh, about 2/3. About two.
Right now, I'm muted.
Yeah, for the per unit too. It's like 0.666 repeating or something. It was close to that.
It's not far away, but what I got is 3/4. Closer to 3/4. Anyone else got any different value? A little bit. Whoa. Two students got 0.6666. Well, maybe. But anyways, the number is a little bit tricky. That's true. But all right, let's see the solution together. Okay, let's see the solution together here. I'm using the black. The system one obviously a little bit complicated due to the given is what? Be very careful. Okay, this is what? This is P, not S. Okay, this is absolutely very important. Again, feel free to divide your paper into two size. And the first size, system one. Second size, system two. In system one, what do you have first? Well, the per unit is given, right? Is this time is a current. Be very careful. It's different. The current per unit one is 1 per unit. And obviously looking for per unit 2 equals to what, right? Just like this. And then what do you have? Once again, VB1 is what? And SB1 is what? All right, this is the idea in your head. Okay, the idea, the structure need to be very clear. So what is VB1? VB1, you need to read here carefully. So Y connected, okay, source phase voltage, okay, and 179.6 RMS, okay. What we need is RMS, so RMS is good. But what we need is line voltage, so 179.6 times square root of 3 kilowatt. This is VB1, right? This is VB1. Line voltage, RMS, magnitude. Okay. Okay, good. SB1 is what? SB1, once again, the active power is 1 mega. It's 1.2 megawatt. At 0.9 power factor leading. We need to do a little bit module 2 knowledge, right? It's the single three-phase power correction. Now correction, we don't need to do any correction, but here we need to do a little bit calculation about the power factor or power triangle. So first 0.9 power factor leading is giving you a impedance angle of what? A negative 25, right? Does this make sense? I mean, inverse 0.9 give you 25.84. However, this is leading, so negative angle, right? Negative angle. This further give you what? The power triangle is very small angle. Like this, right? The horizontal side of line is what? 1.2 megawatt. What do you need is what? Apparent power, right? Apparent power. 1.2 mega. From here, what we need to do is divide by the cosine negative 24.4 degree. is equals to the three-phase power, right? Does it make sense? When this value is the base value, and we are not involving any angle here. What is it? Angle is supposed to be negative 25.84 degree. However, we are just picking the magnitude and magnitude only, which turned out to be 1.33 mega VA. Does it make sense? Right. So with VB1, SB1, we got, well, IB1. This time, be careful, IB1. Okay, IB1 equals what? IB1, according to the formula SB1, you have a square 3 VB1, right? And then it turned out to be 2.47 ampere, right? Base value. Right. And then with the base value, we got the actual current value, which is equal to the per unit value 1 times base value 1, turned out to be 247 ampere. Again, actual value, ready to be used. Okay. And jump over to the system 2, we still need to figure out VB2 and SB2. So by reading carefully here, so another system with three-phase line RMS, nice. Line RMS, nice. Of 345, angle of 60 degree kilowatt. Our line good, RMS checked, magnitude. That's it. You can't involve the 60 degree because magnitude. And SB2 as well. 2 mega. That's 2 mega. Similarly, we're deriving IB2. IB2, SB2, square root 3, VB2, right? VB2. So IB2 equals to what? 3.347 ampere. And with this new base current, we can derive the new per unit value, right? Actual divided by base 2. And then eventually I got around 3/4 unit per unit. Yeah, Kevin, just to confirm the solution here. Take a look to see any questions. Is everything clear? So Noah, what was your you got it?
I just used the active power. I didn't catch that.
Okay. So be careful. Okay, nice. Three-phase parent power. Okay, so back to where is it? Here. Back to here. You see how many points I can make. I can develop variation, right? So first, the magnitude, you need to be careful. Second, apparent power, you need to be careful. Third, magnitude, once again. And then line, RMS. And also be careful, it's three-phase, okay? This is three-phase. Power must be three-phase. I mean, if I'm giving you per phase power, you need to times 3, right? So many point I can sneak in some traps. Does everything make sense? Any questions? The 2 examples should be the exam problem is very close. Is close following such idea. Any questions?
So you were saying that if we're given one phase power
per phase, like I probably gave you per phase.
Okay, so if we're giving like so one phase, we would need to convert that to 3-phase power. Like if we're given one phase power, one of the 3 phases, we'd have to convert that to 3 phase, right?
Yeah, per phase power is what? You times 3. That's it.
Okay.
Yeah. And also you don't need to worry about a phase angle, right? Because the base power, magnitude only. Any other questions?
And so that's what you mean by saying per phase, not to get that mixed up with per unit. You'd probably say with a per phase power of 1.2.
Yes.
Okay.
Yes. So yes, you need to read it carefully. You need to read very carefully. Read carefully. So the variations. So many point I could make again variations. Any other questions, concerns about this problem? You guys ready for? This is one of the calculation problem. This is one of the calculation problems. The third one. And if you're okay with the sequence, the example 3 and the example 2 in lecture 9, you should be ready for problem 4. And if you're today pay full attention and follow all the way long, then you should be ready for problem 3. Well, guess what? You only have 2 problems to prepare, even if you didn't do anything before this point. Anything I can do more to make your midterm 1 easier?
Well, there's tons of stuff you could do, but
like what?
Reduce the questions, make them easy.
No. Well, reducing question, that's not possible since I have reviewed everything. Can't reduce. My review is exactly what is going to be covered in exam, so I can't break this.
Will we have a cheat sheet on the exam?
Sure, as usual. We already have questions out. What does that mean, Daniel? You told what will be in the exam? Yes, I have. You mean exactly? exactly same problem? No. I cannot do that.
Would it be possible to do another symmetrical
Component?
Yeah, another question about those.
I think example 2, example 3 should cover cover all of the possible variation I could. The only place I can vary, I think it's just here. You know what I mean? But given is either three-phase unbalanced voltage ask you to find a symmetrical component, or the other way around. And after those, I might ask for, because once again, up to 9 components, I might ask any one of them, right? Any one of them. The variation is over there, and here I'm asking three-phase native sequence components. Well, I may be asking for, I mean, this question, I might ask for three-phase positive sequence, right? But once again, there's the three components and just up to 9 components. I might ask for any one or any sum of them. You know. Other example.
Can we go through the note pages for the Y-connected loads and the delta-connected loads? I'd like to make sure that I have the right conversions written down between the line voltages and the phase voltages.
Sure. And we can just write from here, right? You can write from here. So first of all, the Y-connected load. And then you have what delta-connected load, right? Only two. Well, here the Y-connected load. What do you have? The phase voltage. Phase voltage. And times square root 3 with angle of 30 equals to the line voltage, right? It's the Y-connected. This Y-connected load or source. It doesn't matter. What is it? Right? For phase voltage, just the times square root 3 with angle of 30 degrees equals to line voltage. This is a relationship between the line and the phase voltage. Second, you have current. And how about current? The current, you should be very happy, right? What is it? The same current, right? What matter is, once again, not the formula. What matter is, where are they? Okay, you understand who is the phase voltage and who is the line voltage. That's the key. So who is the phase voltage? Phase voltage is the voltage across a per phase load or source. This is the phase voltage. And the line voltage is what? From one phase to another. Or say from one line to another. This is a phase and the line voltage. From this circuit, you can also easily tell they're different. Of course, they're different. However, phase and the current, phase and the line current, or what? Phase current, the definition is here. This phase current. Line current means line current flowing through the line here. Because of the Y connection, I line equals to I phase. They're exactly the same. Similarly, in the delta, right? The delta, what do you have? First of all, the phase voltage, you should be what? Hooray, right? However, what is it? The phase current need to do what? This is a relationship between the phase and the line current for delta. And The key is, once again, you understand who are they. Okay? Understand what you are doing. Understand who are they. That's the bottom line. Okay, that's why I always like giving some multiple choice problems, but not this particular exam. Okay, but still, the phase voltage remaining, the concept remaining same. Right? Concept, phase voltage means the voltage across per phase load per source. Line voltage from here to here, line to line. Okay, and then the phase current means what? The phase current means the current through per phase load, just like here. This is current also through per phase load, current through per phase load. Right? High phase. Line current here, and line current here too. This is the definition remains same. Okay, there's no variation on the definition. That's the only thing that never changed. Okay, the definition, the basic concept, the basic principles. Have you ever heard any tricks or any variation on the KCL, KVL? Right. You always, no matter how you write the equation, gonna be the same equation. That's basic principle, never change. 1 + 1 = 2, and always equals 2, right? Those things never change. Definition is the same. And no matter it's Y connected or delta connected, your feeling should be like the definition remains same, no matter Y or delta. Okay, your feeling shouldn't be the otherwise. And here, due to the delta connection, then the phase voltage and line voltage, they're same. Yeah, they're parallel. They're parallel or same voltage. Okay. These are the three phase basic ones. And this is problem 2, right? This is problem 2 in the exam, and obviously some variations could be also just like the review in the review. I have present this. You have what up to what? Y load, delta load, phase line current voltage up to what? 2/4, 8. Okay, I might ask any 2 or any sum of them, right? 8. Of course, don't confuse with the Y prime load, right? Y prime is derived from the delta load. You need Y prime to be able to come up with the per phase circuit. So if you go back to here and a little bit more about the Y prime. Y prime, where is it? Here, right? Therefore, the Y prime phase voltage is like this, from here to here, right, to neutral point. Obviously, not same as the red one, right? The blue one is not equals to the right one, right? So the phase voltage of the Y prime is not equals to phase voltage of delta. However, what? Who is the line voltage of Y delta and of the Y prime? Line voltage of Y prime is from here to here. Guess what? Same as the phase voltage of the delta. And also equals to the line voltage of the delta. Right? Don't confuse with Y prime. Okay, Y prime is derived from the delta. Okay, derived from the delta. Yeah, maybe I might ask one question or two about Y prime. As long as you're clear on this concept, you should be fine too. Okay. Y delta Y prime. Okay. Is that thorough enough answer?
Yes, that was very nice summary. Thank you.
All right, thank you.
Quick question. What was the impedance conversion was 1/3 of Z delta for Z prime?
1/3 of. Oh, here. This is here. So this is Z Y prime, right? And then the red is Z delta, right?
Right.
So what we have is Z Y prime equals to 1/3 of Z delta.
Okay, that's what I thought.
Yep. And when you do this, yeah, you need to divide by 3. You need to divide by 3. This is problem 2. This is problem 2. And if you involving the green color Y prime, guess what? You have what? 3 by 4, 12 variations. I could ask any one or multiple of them, right? Plus power. I'm gonna ask for what is three-phase power of the delta, 3-phase power of the Y. But by the way, what is the 3-phase power of the Y prime? How to find the 3-phase power for Y prime? What was it?
Still, isn't it 3 multiplied by the phase RMS and the I phase RMS?
Correct. No problem for that. Actually, my question is now very clear. But just to realize that the 3-phase of the delta and the 3-phase of Y prime, they're what? Same, right? Does it make sense? Otherwise, it makes no sense. I mean, your Y prime is out of the delta. You can't change anything. Your power will remain same. Otherwise, it makes no sense. Okay. Because Y prime is derived from delta load. So if you already know the 3-phase delta load, and then the 3-phase Y prime load remains same. Make sense? Okay, this is what I mean. Okay, just being aware of this. Being aware of this. Okay. This is problem 2. This is problem 2. Problem 1, I think the quiz problem seems you guys did very well. And hopefully it's really very well. And so should be fine. Okay, should be fine. According to the experience from past years, exam one, the time length is tight. So you want to be hurried, okay? You want to be hurry up. You want to be hurry up. And what else? Oh, a little bit this. I think we still have a little bit of time. So a couple of small things. So one thing is I saw in the homework problem 2.16, the textbook. I really hated that the textbook solution here is very bad, in my opinion. Very confusing, at least. Hopefully, you are not affected. What I'm talking about is this problem. Homework. And this is a problem. Well, basically, almost the same as our in-class example. However, what I want to say is minor thing. You can look at the source terminal. They're labeled as, well, lowercase a through c, right? Look at the load, labeled as lowercase a through c as well. However, be very careful. They're absolutely not the same node. This a and this a, there's no way to be same node, right? That doesn't make sense. Be very careful. Okay, this textbook is misleading. Does it make sense? This is absolutely not the same node. You can't do this. This is a capital A through C, a lowercase a through C here. Okay, that's the one thing. Another thing is receive the question about the base current. Base current formula, first of all, is equal to, what is it? I never memorized the formula here, but anyways, it equals to base power divided by square root 3 times the base voltage. There's a reason for this formula, okay? But we just didn't have enough time, but we do now. So let me derive this. So first of all, you know this is what? 3-phase power, right? 3-phase power. You know this is what? Line voltage, right? Remember? So why this the formula is like this? First of all, the 3-phase power need to divide by 3 to have the per phase power, right? Or per phase power in terms of magnitude, okay? Again, because we are talking about base values, so they're all representing magnitude and magnitude only, right? Per phase power equals to what? Per phase current times what? Per phase voltage, right? Per phase voltage. Then what is a per phase voltage? You need to do this, right? The line voltage divided by square root 3. Doesn't make sense. So your base current here equals to what? Once again, okay, I'm not saying this. I'm not saying this. This is wrong. Okay, because you're missing the conjugate here. Be very careful. This is wrong. But here, what I'm saying is base values. I'm doing operation along base values. That's why I'm not using the conjugate, because it doesn't matter. It equals what? Divided by 3 VB divided by square root 3, right? That's how you got here. This is how you got here. Okay. You got a per phase power divide by per phase voltage. So this is a little bit derived. Probably doesn't matter to our exam, but there is a reason behind. Okay, there is a reason behind. All right.
What happened to your 3 there?
Say that again.
What happened to your 3? You have the root 3, but you have the SB over 3.
Okay, let me.
Or are you just saying that's a 3-phase right there?
You mean here, right?
The square root of 3 over 3 is 1 over the square root of 3.
Yep. Okay. Thank you.
Is it better?
Yep.
All right. Go. Any other questions? Any other concerns? I think there's minor thing is the test run exam, the attendance rate is still terribly low, but probably you guys already ready or have no trouble with it, and hopefully it's true in the exam as well. But anyways, I think the only significant thing is the very last question here. So about the use of MATLAB. The final project of this class obviously used MATLAB to do. Well, I'm glad to see only 2 students, well, out of 14 only, saying I haven't yet even think about it. Well, you should. Okay, you should start to do it and start to think about it. And the MATLAB solution from the school ITS said that they're still working on it, and the bad thing is that they're not guaranteeing availability before the end of the semester. So are we going to rely on it? At least not quite safe. So you need to think about this. You need to really think about this. Either purchase the student's license or just because let me see the due date, because the due date of the project is way before, not way before, but is right before the Thanksgiving shutdown, right? Because from Thanksgiving on, everything is shut down. You can't come back to campus to use computers here. But the time for you to conduct the project is what? Way before it, right? So the bottom line is you have the option of on-campus computers to do this. You understand what I'm saying here? Okay. So the bottom line solution is use the on-campus computer to do this project. Okay. So you need to figure out which day you need to come on campus if you don't want to purchase yourself. The school might provide the student license whenever they're ready. That's all I can say. Other than that, I'm not sure actually, because the department has been requesting this for years. So, all right. Any other questions?
So when will be like project will be available on the module?
When?
Yeah, like
I thought I just presented. Here. Is that clear now?
oh okay, yep.
So regarding the module, is module 4, which is the next module, okay, which is the next module. After the midterm 1, we can start that module.
Oh, okay, thank you.
Yep, sure. And here is question: when will you post the final project? Okay, I think I just answered. Sure. Any other questions? Once again, last question to you guys. When is our midterm 1? When is it? Good. Receive a answer. 3:35. Okay, to most of you. I accommodated one student by another time, but most of you guys. 3:35. Okay, 3:35. Once again, 3:35 at October 7th. Okay, Wednesday, October 7th. 3:35 to 5:05 is the exam time, and the 5:05 to 5:20 is the uploading the handwritten works. All right. Well, yep. Kevin. Yes, that's right. That's right. Okay. So thank you for attending today's lecture, and good luck with your exam 1. Okay. All right. Bye now. No problem. Thank you.